Good morning, my dear students. In today's class, in the chapter Electromagnetism, we are going to discuss the numericals on the Biot-savart law. So, if you can look at the previous class, we earlier to that one. The first we started the theory, and previous class we had some 3 or 4 numericals. We have brought it like the field due to plane spiral, then due to a sheet. This one. Today we'll explore few more current carrying structures and how the field due to this. I think this will be some sort of like a very base for electromagnetism, because if you look at any electromagnetism question, we need to describe the application, we need magnetic field. And who are going to produce such a magnetic field? The current carrying structures. So now knowing the magnetic field due to different current carrying structure, I think this will be like a fundamental thing. And if you know how to calculate field, the application part will be very easy for you. So in advance, you are having 2 types of questions. One, they're asking the fundamental, how to calculate field due to various current carrying structures. And next is asking the application part. So in either way, I think this particular topic will definitely help you a lot. It is similar to like in electrostatics, finding electric field due to a charged object. So I suggest you like students to explore all the possible current carrying structures and be ready for exam. You'll be on safer side. Okay, let me start the class. So if you look at in examination, they're asking very simple structures and also some very like a calculus based one. So you must be in a position to analyze either of them. Let me take a structure. Not visible. Okay, we have a current carrying wire. Okay, the wire, it is bent. It's a long wire. I will bend it. And on the bisector, you have to find out the magnetic field. Okay, let this be the current I. This is very important, can be asked even in advanced exam as it is. So we have to find out the magnetic field strength at point P. Okay, let this be at a distance A. This much of information is there. Find the magnetic field strength at point P on the bisector of this long wire at a distance A from this bent. I'll write it here. Find the magnetic field strength at point B. You have to calculate the field strength at this particular point. There's a very fundamental one. Already we know formula. We are aware of the basic formula due to finite wire. What formula we were using to find out the magnetic field, no, the same formula has to be applied here. Let me make you to recollect. So if you know for a finite wire, if this is the I could have directly solved it. You'll be in a big trouble. Okay, there's a finite wire. Current any direction. Okay, let it be here. What are alpha beta? Angle made by the line joining the end with the point P. Angle made the line joining the end and the point P with this perpendicular distance. Okay, this was the alpha, no? And similarly, beta, the angle made by the lower end, the angle made the line joining the lower end and point P with the perpendicular distance, and that is what this beta. Okay, now what was the formula we arrived? It was magnetic field equal to mu naught I 4 pi d sine alpha plus sine beta. Any conditions for alpha beta? Yes. Alpha, if it is measured in this sense, it will be positive. Beta, if it is measured opposite to alpha, it should be taken positive. Look at the sense of the measurement. And this is what that alpha and beta equal to 0 degree line, this one, this perpendicular distance. Now, the same formula has to be applied here. We have to calculate the field strength at this point. If this A is a perpendicular distance, the answer is no. So bring the perpendicular distance. Let me bring a perpendicular distance. Okay, this is what? 90 degree. Now this will become perpendicular, not A. No, from the all, 45 degrees. So this will be 45 degrees. So this will be 45 degrees. Okay, first we'll study for one wire here. Now from here, okay, I think I'll do first for this wire. It'll be easy for you. One problem if you can understand, the rest all you can manage. Only one problem of this kind. Okay, this angle, this will be 45 degrees. So this will be 45 degrees. Let me keep it in this way. Yeah. Now, this is what that perpendicular distance. Then how we define the alpha and beta? How we define alpha and beta? Angle subtended at point P it is. We have to define this alpha and beta with respect to this one. So you can see now what is the angle made by the alpha. Will this work out here? I think we have to produce it back now. We have to produce this back. This will become alpha. This will become alpha, and this will become. So this is the thing. So at point P is there. So now look at this one. The point P we have to produce. So in this, shall I define alpha beta? Again, it will not help you. This will become. This line will not help you. So we wanted perpendicular distance. So produce it back like this. This wire you produce it back. Just extend this one. Then bring that perpendicular distance. I'm showing it here now. This may not, I'll come to later on. Okay, now this will be perpendicular distance for this wire. I'll call this is wire 1. Wire 1 or to any number. Now, what are alpha beta? We have to define alpha beta. So to define alpha beta, I will go for like this. Now first, what is alpha? Alpha is this one. Then this is beta. This angle 90, this angle will be 45 degrees. Is it alpha positive? You just rotate this, keep this wire somewhere in this direction. So what is alpha? Alpha we measured in its actual direction. And what about beta? Beta we are measuring opposite to that, no? And how much it is equal to beta? 45 degrees. So here for the wire 1, alpha is 90 degrees, beta is minus 45 degrees. Why negative sign? Because if beta measured in the direction of alpha, it should be negative. If it measured opposite to alpha, it should be positive. Then perpendicular distance, do we know? We don't know that one. So how to calculate that? Sine 45 is equal to D by A. D equal to A by root 2. Okay, let's write down the formula. Magnetic field strength at point P due to 1. This should be equal to mu naught I 4 pi d sine alpha plus sine beta. Everyone, please do put effort to understand. One problem is enough. You can manage most of the numericals. So this will be 90 degrees. Sine of 45 degrees. So the mu naught I 4 pi, this will be 2 root 2 pi a 1 minus 1 by root 2. What about the direction? Into the plane. This is due to wire 1. Field at point P due to Y. Similarly, I want due to Y2. Due to Y2. So again, I'll take help of the same diagram. Let me show it separately. It'll be easy for you. Oh, where it has gone. I'll get it back. I think, okay, no, we'll erase all these things. Fresh, we'll start it. Now, due to Y2, all of you look at this Y2, the same method. So what is the method? Extend this line. Extend this line. Then perpendicular to that. Okay, this will become D. And we know this is 45 degrees. 45 degrees. Then this angle will be 45 degrees. What about alpha? Alpha is, I had to bring alpha, no? So the alpha is something, this one. So this is what alpha. Oh, everyone is able to get that. And this is the beta. So you're measuring alpha. No problem. Like alpha is positive. What about beta? Beta measured in the direction of alpha. So therefore, what we can put beta? Beta will be negative. Then again, what is the value of D? Sine 45 is equal to D by A. So D is equal to A by root 2. Beta equal to minus 45, alpha equal to plus 90 degrees. The formula, the same formula, BP2 due to Y2. The magnetic strength at point P due to Y2. This should be equal to mu naught I 4 pi D sine alpha plus sine beta. If you want to give some other symbols, alpha, beta, you write theta 1, theta 2. Alpha dash, I'll write it. Some of yours are same alpha. Okay, no, alpha dash, beta dash. Okay, no. So mu naught I 4 pi A by root 2 1 by sine alpha. This will be 90 degrees. 1 minus 1 by root 2. What about the direction? Can we go for direction? It will be into the plane. So net field at point P, I want now, has to be found out. So BP1, just shall I both are in same sense? Okay, I'm going to add up. So final answer will be 2 pi A root 2 minus 1. I'll show the complete problem. Getting that, so that defining that alpha beta is something very, very important for us. Why we are discussing all this? Is it really worth it? You do have many, like a wire, no, which will have a bend in applications. At many places, what when a necessity arises to bend a wire. So when you bend a wire, okay, what can be the magnetic field at various points? As we can use this method. Nothing is here stupid. Is do understand? So almost all the numericals. So if I make numerical, maybe it is of no use because I'm not a practical person. But in all the standard books, what are the numericals are there? They are somewhere used in the applications. I'll take the next one. This will be carefully try to we'll try to draw a better diagram. This also. Okay, this is the point P. There we have to find out the magnetic field strength. So what is the information available? The information available for us is this distance is what available. These angles, I'll define it. 30 degrees. You have to find out magnetic field strength at point P. Okay, let I be the current flowing in the wire in this way. Okay, start analyze now. Find the magnetic field strength at point P. Very good problem. Very good problem. Almost all the basics are being covered very systematically here. So shall we break up this into this long wire into segments 1, 2, and 3. What about the field strength at point P due to 1 and 3? Should be 0, no? Because the point lies on the axis. According to the Biot-savart law, it should be 0. So the point lies on the axis. So the field strength at point P due to 3 and 1 will be 0. At point P, B1 equal to B3 equal to 0. The reason for that, because the point P lies on the axis of the segments 1 and 3. As the point P lies on the axis of segment 1 and 3. Segments, part of a wire called as segments here. Now, what all the field strength is only due to this wire. What is a method? Okay, I'll extend a line. Okay, this is the perpendicular distance, no? And then after that, we have to define that alpha, beta. Alpha, beta. So I'll suggest you, why don't you, if this is a wire, there's a perpendicular distance, let's assume that one. Then, so what you're going to do, it'll be off like this. How you define alpha, beta? There's a finite wire. How you define alpha? If you define this is alpha, this will be beta, no? See, what is the biggest problem? Nobody wants to do artwork here. Means like this somewhere, one other diagram drawing. Everyone wants to do smart thinking. Smart thinking is not possible in the scientific world. So students nowadays, what happen are going mad with what? Tricks, okay, shortcuts, all that one. Maybe some small exams, okay, board exams. But when you go for competitive exams, better have a solid knowledge first, analysis. So everyone is bothered now, like in a very less time, how I can prepare more. I think there is what you're killing your thinking ability itself. Forget about rank, that one. Maybe some small exams, okay. But at least advance, you should not. Even JEE means advance, nothing will work out. Even the mains exams also, the questions are not based on shortcut and tricks. State board exams, okay. The tricks and all will work out. So please, that's why I'll never introduce any shortcut or tricks. That's nothing but like you're trying to avoid thinking. Am I right? If a student develops on his own, okay. But not like something it should be taught. This is something very important in the teaching field. That's why you see that the earlier professors, they never bothered about teaching shortcuts, tricks and all. But nowadays teacher, like they're more bothered about teaching shortcuts than imparting knowledge. I think there the real mess is what being created. Okay, don't ask me any shortcut tricks. Just only we know science. Huh? Okay, no. Why don't we compare? Okay, shall we do like this? This, I'll bring it here. No, this is something alpha, no? And this is beta. Okay, but here let's come for this one. This is what alpha. What about beta? Beta is something, here it will come. And how much beta? 60 degrees. So there is no problem with the beta. Beta I'm measuring in the sense in which it should be measured, but alpha I'm measuring in opposite sense. So this is the line, reference line. Alpha is what? I'm measuring in opposite sense. Looking at the arrow, are you able to compare? I think if you can draw this diagram, it's very easy. Okay, let's get into the formula now. The magnetic field strength, BP equal to B1 plus B2 plus B3. This is 0. Due to 2, it should be mu naught I 4 pi A. A is that perpendicular distance. Sine alpha plus sine beta plus 0. What is alpha? Let me define here. This will be minus 30 degrees. Beta will be plus 60 degrees. sine of minus 30 degrees. Sine of 60 degrees. So mu naught I 4 pi A mu naught I think this will become 8 root 3 minus 1. Any possibility of direction should be out of the plane. Sir, how come you say out of the plane? I think from the vector cross product, the resultant field should be perpendicular to plane containing current element and R bar. So where is R bar? R bar is this one, and this is a current element. So what do you expect the B bar at this point? Should be out of the plane. Okay, so many questions are there in the book of different nature of like this. So if there any bends are there, okay, don't get bothered. Stick on to the basics here. How alpha and beta are measured, in what sense they are measured. This is the y-axis, x-axis, this is z-axis. So let me bring certain. Okay, we have, okay, let me bring the wire. No, a current flows. That just a problem is very simple only. So what you mean to say is like a different parts, now they lie in different segments. Also different planes. You have to find out the magnetic field strength. This is lying in some XZ plane. This quarter circular arc lies in XY plane, and this long semi-infinite are also in XZ plane. So we'll break up this into 3 parts: segment 1, segment 2, segment 3. We'll find out the field individually at origin, then we'll take the vector sum. So different parts of the wire will lie in different planes. So how to get the resultant field? This was the question asked here. So the resultant field, first B bar equal to B naught equal to B1 plus B2 plus B3. B1, it's a semi-infinite wire. So what is the formula for semi-infinite wire? Mu naught I 4 pi D sine alpha. Okay, this R will come. Due to long wire, it will be 2 pi R. That's a semi-infinite wire, no? So directly I'll write 4 pi R. Is it justified directly writing this one? I need not to write sine alpha, sine beta, all that one. What about the direction? How it will be along negative y-axis, J cap. Due to arc, what is the formula? Mu naught I by 2R theta by 2 pi. Theta is what? Angle subtended. How much? Pi by 2. What about the direction of this? So it is in XY plane. So minus K cap. mu naught I 4 pi r. This will be minus k cap. Mu naught I 4 pi r I'll take common, so minus j cap. Here theta will be pi by 2. Pi we cannot take outside. 4r I'll take. Theta, if you substitute, pi will get cancelled. So this will be minus k cap. So mu naught I 4r minus j cap by pi. Okay, see this. So this will be the magnetic strength at point 2. So you may get a numericals of this kind where the wire segment lies in different plane. You look at the advanced or mains paper, no, they're very popular. Very simple questions are also there. I'll go for the next one. We have to just go for the vector sum. Pi by 2. Theta substituted here. Theta substituted, pi get cancels. Okay, 2 will come here. Okay, for this 2 will come then. Oh. 4 we took it, no? 1 2. Okay, check now. Theta substituting, so mu naught I 4r will yeah, 1 2 will come. I made correction here. Now let's take the one more. So let me send a current. This will be the radius. So we have to find out the magnetic field strength. It's at origin due to this current carrying structure. This is a long wire, semi-infinite wire. This is lying in exact plane 1, and this will lie in the same exact plane, but it will be parallel to x-axis. This will be parallel to z-axis. Okay, start breaking up into different segments. Okay, take help of now. The segment lies in YZ plane. This will be an XY plane. XY plane, sorry. Okay, shall we give number? So we'll start with the numbering. 1, 2, 3, and let me take this is 4. I think this will become unlimited way of asking questions. I think the student has to learn some methodology, then immediately think on different 5, 6, 7, 8 problems, then go for some other concept. There's no fun in working some 100, 200 numericals in this in this particular type of questions. Please keep in mind. Magnetic field due to 1. Mu naught I 4 pi r. And how it will be directed along y-axis. Magnetic field due to 2. Mu naught I by 8r, because due to quarter circular arc. Due to ring, mu naught I by 2r. Due to semicircular ring, mu naught I by 4r. Due to quarter circular ring or quarter circular arc, it should be mu naught I by 8r. And how it will be along z-axis, k cap. Next, B3. It lies in YZ plane. So therefore, mu naught I by 8r I cap. Then semi-infinite wire, B4, mu naught I minus j cap. So these two will cancel out. The net field will be only due to 3 and 2. Field at origin, net field at origin. Anybody having doubts, you can clarify. We'll go for the next current carrying structure. Solenoid we'll discuss. This is this solenoid. This is called like a this is called as a inductor in the next coming chapter, EMI, electromagnetic induction. No, I'm going to give a name. I'm going to call this as like a inductor. The thing, and solenoid will come of different varieties of wide varieties of shape. The wide varieties of shape. So like how to calculate the magnetic field due to the different types of the solenoids is what one of the very popular way of asking questions. So as when we go to Ampere circuit law, we are going to discuss like another 2-3 different types of solenoids called as toroid and other situation. No, time being a basic solenoid we'll discuss here. So what actually a solenoid will be? So it is like I'll take some spring, best example, closely spring. Best example is what I can give it as a spring, that one. So if you look at the I to show the diagram is not there. I'll get the diagrams. These are some different shaped solenoids are there. Just type in Google, you will get plenty of things. Most popularly, what we use in the lab will be of this kind, copper winding. These are used in circuit. So then circuit boards it is used. Circuit boards, like you open mobile or the television or any of the electronic circuit, there it will be of like this. This is more popularly what we use in electrical equipment, toroid. This is used in small gadgets. used in gadgets here. So we have plenty of types of solenoid. What we will discuss is of this one. Later part, okay, for different shaped, how to find out the magnetic field. Solenoids again of n number of shapes are there. The basic cylindrical solenoid is what our syllabus is there, and toroid is what in the next Ampere circuit I'm going to discuss. You don't bother these things, very difficult at your level. Only these two are a part of syllabus. Some slightly modified, I'll bring into the picture. Got the idea now? This is what we are discussing. Sir, I want to construct a solenoid. Do one thing simple, take a wire, take copper wire, wound on your finger, make it like a spring. There is a solenoid over, and you have to wound it very closely. You see, there's no gap between the turns. But how comes a short circuit will happen? For that, what we do is first I'll wound one turn. So what I do is one turn, I'll wound it. Like this. Then I'll apply a insulating layer. It's not that easier. So insulating layer, I'll apply it. Then again, one more turn will be wound. So here, to show you, I'm bringing this gap. I'll just take a liquid. You just go to the Hyderabad nearby, Opal side, no, we have some industries. That one Nacharam there. You just visit there. So there's a ferrite rod. What I do is I'll take a wire, I'll put one turn. Then one brush will be there. I'll dip in a liquid. That's the insulating one. I'll just color it. Means I'll just paste it that liquid. That liquid is an insulating one. So though these two turns are in contact, but between them what happen? An insulating layer will come. Then again, I'll bring the insulating layer. So now actually they're in contact, but between them a gap, a liquid layer will be brought. Insulating layer will be brought. So like that, they'll be very closely wound. If you look at the practical, you feel as if they're in contact, but in between a small liquid, I'll take a brush, I'll just put like this. Then I'll wound another wire. So what you do is take a wire, just wound on your finger very closely that the turns will be in contact. When you're wounding, what happens? After wounding one turn, you're going to apply an insulating layer to the wire. Then you are going to put another turn so that it will come in contact. So like that, almost the gap will become negligible. Very closely wound solenoid. If there is a gap between turns, it's not flux leakage, it is called it, and no use for application. You can see in all, hardly there is any gap. Getting no? This one. So like this, it will be wound on some ferrite rod and become a solenoid. And very, very important. In fan, the solenoid, in the water pump, all electrical equipment, the solenoid is what the basic element. So we have to find out the magnetic field due to a cylindrical solenoid. So this is what I'm going to discuss here now. We will discuss on him. Okay, or him. We'll study this. This will come other types of solenoids later part. I'll introduce them. Okay, there's a thing. So how to every time drawing this will be a big headache. The solenoid here. So therefore we have brought in a circuit symbol. So what is the circuit symbol? So the field actually they're very close. I'm showing it to make you understand diagram. We are bringing in this way. This is one solenoid. First, we'll define the axis of solenoid. Here, what is this? This is a 1 turn current carrying wire. I to. This is for our understanding purpose. It will be like this. I'll wound in this way. They're very closely wound to make you understand. I'm just showing some gap. Please do understand. It'll be like this. So if a current flows here in this direction, so definitely, what do you expect? I think that you are going to bring this structure here. Hope everyone is able to understand. The current here is entering, and at lower part here, the current is coming out of the plane. Is it okay? The showing the dot. Hope everyone is able to understand now. So now, sir, what about this solenoid? How you are bringing? Same thing. I'll just bring the current in opposite sense. Your current will be in opposite sense. Look at everywhere. At a few places, I'll show it. So every time drawing this solenoid, all that one, so we have brought this is a symbolic form. Now, shall we assume this to be like a ring? We know magnetic field due to a ring. So how the lines of force will be? The lines of force here will be this will be the lines of force. Similarly, what about the lines of force here? The magnetic field lines of force. So from the concept of ring, previous class I discussed the ring. That is what you have to bring it here. This will be the B bar inside the solenoid. So every time, and the solenoid will have some finite length. This is what the L is what we define. And it's having some n number of turns. Is having n number of turns. So what is the basic feature of solenoid? Number of turns per unit length. N is number of turns. What is L? L is length of solenoid. So then we'll define N by L. So this will be defined as number of turns per unit length. So we have to find out the field strength due to this particular solenoid here. Hope everyone is able to understand. Okay, let's do one thing. We will try to find out the field due to solenoid. Okay, this is called the axis of solenoid. Okay, now start thinking how you can find out the field due to field inside the solenoid. Any method? I'll just highlight this thing so that it'll be. Below one is a physical diagram. The above one is a circuit symbol, like a resistor. We used to show zigzag line, capacitor, two plates. Similarly, solenoid, we use this particular symbol. Later part, we are going to replace with a coil, just like with a spring, similar to spring. This will become a solenoid, or it is called as an inductor. In the next coming chapter, EMI, how resistor, capacitor, like this inductor is also very, very, very important. The whole one chapter revolves around this particular solenoid here. Now we have to find out the magnetic field strength on the axis of solenoid. Okay, I think make observation. I will go for the derivation part. We have to derive the magnetic field due to solenoid. Let me assume it's a very good application part of the problem. So we do expect students to really put effort to getting the magnetic field due to solenoid. No, these are the into the plane circles. There'll be plenty to make the problem little bit neat diagram. I'm showing the spacing between the turns. Okay, choose this point. Here at this particular point, you have to find out the magnetic field due to solenoid. So the same thing, n number of turns are there. So let L be the length of the solenoid. Capital N be the number of turns. Number of turns per unit length will be small n. I'll have water. Meanwhile, you can try. So what I suggest is like assume small element, elemental strip. Let it contain dn number of turns. So let this be dx. There's a very standard derivation. Again, don't expect anything new because what is there I should derive. Okay, let it contain dn number of turns. Okay, this turns, I should show it here only. No? Dn number of turns. So this will behave like a ring, no? Okay, able to understand? So in that small width of dx, there'll be dn number of turns will be there. It will become like a similar to coil. And so let this be a distance x. At a distance x, this point P will become like an axis where we are supposed to calculate the magnetic field. Then let me define these angles here. Some other color. Yeah, I am changing it. Let me define this thing. So this will be the one reference line will pick up. No, I'll define this one. So let this be the beta. Both are into the plane. Oh, yeah. Okay, fine. Thank you. I'll do correction. No, let me define these angles. Let me define this is beta. Let this be alpha. And let this be theta. This is d theta. What is use of that you can see. First we'll define the, shall we say this is like a ring? What is this yellow color strip? Like an elemental ring of dn turns. If you can understand this, the problem is over. So what is the magnetic field at point P due to this elemental ring? Magnetic field strength at point P due to elemental ring. dBp should be equal to mu naught. Go back, dn number of turns, the current, how much it should be? The current should be equal to I. Let I be the current flowing through this. Then radius of this r square. Elemental ring or coil, anything you can you can write it. Coil or ring, it doesn't matter here. Elemental ring of dn turns. Okay, or you write coil. Okay, mu naught I r square. So this will become r square plus x square to the power of 3 by 2. I think there's no problem. We are able to get this equation. What is dn? dn should be equal to n into dx, number of turns per unit length into dx. So small n is what? Number of turns per unit length. So dn, I'll go for mu n is equal to n into dx. I r square plus x square to the power of 3 by 2. So let me define few terms. Tan theta shall we define as x by r. Anything find difficult, just bring triangle and work out. Tan theta, I'll write as x by r. Then we'll try to replace all the terms. So I want dx r secant square theta d theta. So dx all everything I can replace. No, so the field strength at point, this one will be mu naught n. Dx will be r secant square theta d theta into I r square will be 2. 2 is missing, 2 is missing, 2 is missing, 2. R square, x square will be r square tan square theta. So mu naught n I r cube okay, this will be secant square theta d theta, here 2. R cube will come outside. 1 plus tan square theta 3 by 2. R will get cancelled out. So mu naught n I by 2 secant square theta d theta folded by 1 plus tan square theta secant square theta. I'll end up with secant cube theta, or this will be mu naught ni by 2 cos theta d theta. This I'm going to go for limit. Anybody, what should be the limit? So this is the theta equal to 0 degree line. So minus beta 2 plus alpha. Cos alpha. So this will be minus of cos beta, will be cos beta only. Sorry, sin alpha. After integrating and substituting limit. Okay, there's expression for magnetic field inside the solenoid. What are alpha, beta? How you define alpha, beta? There's expression. So using this formula, now we can explore inside the solenoid. Just see once, I'll go to the, because there's a possibility of all way of asking inside the solenoid to some way to get the magnetic field. I think chance of asking in advance derivation ruled out. No, advance means only the formula is what you have to remember and the application part. I'll go to the next one. We'll explore here inside the solenoid. What are the conditions? We'll have this much of formula. Let me take the solenoid. What are that alpha beta is what we should have a clarity before going for using that particular formula. Okay, this is the axis. We need to, I can define wherever I want the axis. So let me bring the point P here, somewhere very arbitrary. Then this will be the alpha and beta I'm going to define. Anywhere, it may not be on the axis here. The formula has become now generalized. So this will become beta. This is alpha. Then what you're going to write this as y1. If you take this is x1, so this remaining distance, this will be L minus x1, or x you write it, y x1 whole. And this total length of the solenoid is L. Again the same, that current element is what you have to show it. See this here now. So what are alpha beta? How you bring alpha beta here? I think it'll be quite easy, no? Sine alpha. Sine alpha, you're going to define it as L minus x by, what about sine beta? Sine beta will be x by root of x square plus y square. So by varying, by moving the point P anywhere, you are going to find out that alpha beta. That alpha beta, you're going to substitute here. So we'll get a field. So what do you expect the field strength inside the solenoid? Uniform or non-uniform? Anybody wants to reply? You know, triangles, everything, so many ideas. Field inside the solenoid will be uniform or non-uniform. Look at the as you vary x and y. Definitely the alpha and beta will be different. So what is the field inside the solenoid will be non-uniform. That too in a short solenoid. So for a short solenoid, this formula is applicable for short solenoid. Okay, this is what all I am discussing here. It's a short solenoid. For short solenoid, how to calculate the field, there's a particular formula. And what about the field inside will be non-uniform. How you say short solenoid, long solenoid? It all depends upon the radius. So for short solenoid, what is the condition? For short solenoid, L will be less than R. We don't use in applications. I'm making things clear. We don't use short solenoid. L will be less than R. Then B bar and the B bar inside the solenoid will be non-uniform. How to find out it? We have a formula. It is not much used in applications. I'm making clear. So therefore, there are no questions much available here. If anybody asks, find out the field inside the short solenoid, I think there's a big problem. I don't know like what applications used. As such, I have not seen where it is used in application, to be frank. We prefer the long solenoid where the field is uniform. Next, again, we'll go for the long solenoid. For long solenoid, the field inside will be non-uniform, and how it has become non-uniform, we have to justify. Okay, no. Okay, this, let it be into the plane. So they'll let this be out of the plane. Why we are giving so much of importance is like we have one chapter itself on like how capacitor, no? The same thing, the solenoid. So therefore, a best idea of this will really help us a lot in the coming numericals. So how do we expect the field? So out of the plane. So let's draw the lines of force. So the lines of force here will be the field here will be uniform. Okay, how do we define long solenoid? If L, if this is the radius, if L greater than R, suppose the length is say some 30 centimeter, radius is say like a 2 or 3 millimeter or 0. Or so like a 1, or even 1 centimeter, then become a long solenoid. And the field inside the long solenoid at the middle, it will be uniform, not everywhere. Field at center and nearby it will be uniform. Okay, this let's go for one more. Exactly at the where will at the ends we'll see, we'll calculate, because we have a formula also. No, exactly come for this. Here at the ends, it has to be determined. Okay, what is the method? We have to extend a line, and this will be line, no? What is alpha? Alpha is 90 degrees. What about beta? 0. So, sir, how you are drawing all this one? So go back. Alpha, beta. Okay, at least I think I want everyone to look at this diagram. Here, this diagram. I think at any point we define alpha and beta, no? So what is a beta, no? So the beta will become 0, and this will be the alpha. And what we have put it, L very much greater than R. So what do you expect alpha? Alpha will tend to 90 degrees. Then the formula will become Vp equal to mu naught Ni by 2. Where is the point P now? Point P, where it is? Now it is at the ends. What is the magnetic field at the ends of the solenoid? It is mu naught Ni by 2. Means somewhere inside will take it. So what is alpha, beta? Both will tend to 90 degrees. Then how much field inside exactly the middle will be mu naught Ni. Somewhere here if you take it. So alpha, beta tends to 90 degrees, and the field will become like a uniform mu naught Ni. Then as I move from the center, somewhere in this region, it will be uniform. Then it starts decreasing. Then at the ends, it will become mu naught Ni by 2, and outside again it starts decreasing here. So field inside the long solenoid, nearby center, how much it will be? Mu naught Ni. Field at center nearby, it will be uniform and is equal to mu naught Ni. Alpha, beta tends to 90 degrees. For long solenoid only is again, please, it's not a short solenoid. For long solenoid, field nearby center somewhere here, the field strength will be like this. For same long solenoid at the ends, how much will become? Mu naught Ni by 2. So with this, okay, now we have certain firm idea. So what about the field strength inside the solenoid? How do it will vary? Means now we can plot a graph itself. Now this graph is very important. The variation of magnetic field strength. So the curve will be I have to bring solenoid also. Little bit lengthy. Only the derivations are a little bit lengthy. Once we get it, then we can enter into the numericals. No. So what is the physics drawing diagrams will take more time. Yeah. Okay, the field strength here it is mu naught Ni. Okay, now you can see clearly where it is at the somewhere in the central middle of the solenoid, somewhere in this region, it is uniform. At the ends, mu naught Ni by 2. You can see clearly now curve. I'll draw exactly the curve. Okay, now we ended up correctly. Okay, got this one. This is very, very important. Okay, still most of you will be having a doubt. I do agree, but I don't know why nobody is asking this. I wanted a very beautiful question in the solenoid. Every year, it's not that every year a teacher do wait. He will wait for that particular beautiful question from the students. Teachers should not ask, actually students were supposed to ask. Now, okay, this is about the field somewhere nearby center uniform, and as you move not at center, you can see this nearby centers at center and nearby center in this region it is uniform. Then as you start moving, it start decreasing. At the ends, it will become off that at the center. So now if at all I'm using for application, I'm going to use this part of solenoid. Are you able to understand? The more you make L greater, suppose say L is equal to say some 30 centimeter, radius you put 1 millimeter. Yes, definitely open. We can expect this region of uniform and field more. So that's not bothered at all applications, everything. Okay, now what is the field? What is the field here? Why I'm not discussing anything here, field in this region, outside the solenoid. So field exactly outside solenoid here, non-zero. As you start moving away, decreases somewhere at a point, it'll become zero. Okay. Here mu naught ni by 2, here start decreasing, then become zero. So there'll be field here. Let's talk about here. So what about the field here? Mu naught ni by 2. As I move away, start decreasing. Suddenly will not become zero. What about field here? Why we are not bothered anything about? If this is the solenoid. Okay, meanwhile, think it, I'll just bring a small diagram so that it'll be easy for us to. No, I'm interested in this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. What about the field in these regions? That 5 is far away. Okay, we know field at 1, 2, non-zero uniform. Field at 3 and 6 will be off of that. Field at 4 will be non-zero and will keep on decreasing. At 5, almost some far away, it will be 0. 7 also will be non-zero. 8 and will be 0. So what are the things? Now we'll go for the numbering. All different. B1 not equal to 0. B2 not equal to 0. B3 not equal to 0. B4 not equal to 0. B6 not equal to 0. B7 not equal to 0. What about B5 equal to 0? B8 equal to 0. What about other numbers? Let me ask, what is the lines of force? Magnetic lines of force, are they continuous or discontinuous? They are continuous. They are continuous. So they'll be like this here, no? They are continuous. Then here also there'll be lines of force, but we are I'm going to write very bluntly 9 equal to 0, 10 equal to 0, 11 equal to 0, 12 equal to 0, 13 equal to 0, 14 equal to 0. That's all. Sir, are you sure? As I'm saying, I'm very sure. So, but lines of force will be there. Here, the lines of force will be continuous, no? Will go outside the solenoid, no? Here. Then how come here lines of force is there and you're telling non-zero? You're telling 0. I'll confuse you further with this diagram. I want to really confuse students. Okay, I'll confuse you with further diagram. The lines of force I'll show by red color. This is what actually happens, no? It is such an important element all our electronic gadgets, they do run on this one. To that extent, this element is very important. These are the lines of force. You can draw many here. Lines of force, are they present outside the solenoid? Yes, they are. No, but I'm saying zero. Okay, agreed, all of you. I think that this diagram now everyone will agree. Okay, I have one diagram, and also I'm saying zero. I think there is some problem with your physics teacher. is showing that lines of force are there, and he's writing zero. Definitely, I think some physics teacher brain there is a problem. So anybody? So shall we remove this physics teacher because he himself don't know what is drawing there, because here is saying that zero and here is showing lines of force and is saying both are correct. So I think, so what to do with the physics teacher now? Sri Vignesh, but they exist only to a small extent. What do you mean by that? I'm not understanding what is it. Anybody, if I give Sri Vignesh reason, will you accept? No. I want answer from students, sir, because these are the things which are observation needed. It's quite very simple. What is the radius of solenoid? 1 centimeter, 2 centimeter. Suppose there are some 10 lines of force is what I'm showing here. In 10 centimeter width, if there are 10 lines are there, this is where it will extend till infinity, no? In infinity, 10 lines of force, what is the magnetic field? Will become zero. In a width of 10 centimeter, if there are 10 lines of force are there, now from here to till infinity, I have to go. Then how many 10 lines? So what do you expect now? The distance between lines at this will extend till infinity. The spacing between the lines also will become infinity. If the spacing between lines infinity means almost the field is zero. So practically, if you go and check it, compass needle, if you keep it, no, it will not deflect here. But therefore, in the books, it is understood like a student must think here. So how they're leaving some things for students to have a general conclusion. Sir, book, why they didn't explain like this? There's a common sense, no? In a width of 10 centimeter, like in the width of say like some 5 centimeter, there are 100 lines of force. You take it, no problem. Okay, 10 you feel small number. Let me keep 1,000 lines of force. Then in a width of infinity, 1,000 lines of force. Infinite width means, so what is the spacing between the lines again will become infinity. So what is the field strength? Will be zero. Okay, getting the idea now? So if you keep compass needle here and here will be zero. We asked questions in exam of this kind of matching. 90% of students would not answer. But you ask numerical, find out field strength, everyone is able to tell. So this shows that students are very good in what? Like formula calculations only. They don't want to analyze, they don't want to think. They're so busy in solving numericals and getting answers, solving numericals and getting answers. This is actually basic idea, but this field will become negligible. Though it is present, it will become negligible because in an infinite width, any number of lines, the field strength will become zero. So we just put negligible or say equal to zero. Okay, so this is about the basic solenoid. Now, can we find out, okay, this formula applicable only for field inside the solenoid? Next question comes. No, even you can bring outside also, somewhere here. at 4 or somewhere in this region, you can find out. Let me have one problem so that completely we can wind up this topic. It's a mere theoretical one. An infinite long solenoid having n turns per unit length is as shown. Find the magnetic field strength at point P. Okay, there's a solenoid. Where is the point P? Point P lies outside. Okay, I just picked the problem. Can be asked in advance because in books we don't have anything like this outside the solenoid. So, and the let R be the radius of the solenoid. Long solenoid, infinite long solenoid it is. So here there is a current. Actually, they are very closely wound. So again, drawing the exact solenoid will take half an hour. A rough diagram it is. Now get into the discussion. You have to calculate the field strength at point P. Where is this is the axis. Get into the I think we have to define that alpha beta. To define that alpha beta, what we do, we are going to define like this with a condition with respect to one vertical line. If you are able to remember just now what we discussed. So this is what the beta no, and this is the alpha. What is alpha? 90 degrees here. What about beta? Plus 90 it is. Beta will be minus 45 degrees. Because look at that triangle. This is R, this is R. Tan beta equal to R by R, which is cotton. So beta equal to 45 degrees. So let's come and substitute in that formula. Mu naught. So that formula is applicable even to find out the field outside the solenoid. Very important. In books, they didn't mention. The reason for that, we are not bothered about any application field outside the solenoid. Very rare. 5% of applications are there where the outside the solenoid, I'll be having some use that one. So therefore, the books didn't bother. Okay, don't again think that it's a very good problem. Okay, sine 90, sine alpha, sine beta. Okay, this is the expression for the magnetic field outside the solenoid. Okay, as you vary that point P, no. So now I think it's very clear for you. Field at here mu naught ni by 2. As you move, it will start decreasing. Will not become immediately 0. It keeps on decreases as you increase this R. As you increase the distance, as it starts decreasing. That's what this formula. So what all that graph, everything, I just wanted to give it as a numerical. just mere theoretical one. No? So here we have one numerical itself also. So where the point P lies outside the solenoid. So there's a long solenoid. Okay, yep, we'll take the one more. Okay, this is about the, you have to just remember, it's a theoretical ideas, all this one. Numericals are there, but may not be very important, or what I feel. Let's take the some our simple problems. Now I want the field strength on the, at center, we know it. Hope if you can remember, at center, we know it. I'm unable to. I'll construct it. Yeah, finish. So I want the field on the, I need to draw one more circle. Now this is a semicircular arc. And somewhat a better diagram, I brought it. So you have to calculate the field strength at point P, not at O. Let I be the current flowing in it. Let R be the radius of it. Carry on now. These are some math-based questions you have to be very, very careful. Can be asked in advance. We have to calculate the magnetic field strength at point P, not at O. At O, we know it. Mu naught I by 4R. Take the question, find the magnetic field strength at point P due to semicircular wire of radius R carrying a current I. You have seen such things in the electrostatics also, in the mathematics. So what is the basic method of solving such numericals? What is the basic method of solving such numericals? Like, take the vector form. It'll be a little bit easier. If you do this in the vector form, little bit easier. Start analyzing. I will write one more diagram to explain. What to do for this? We'll assume a current element. Because there's only alternative method available, no? We have to assume a current element. Okay, let this length be dl. We have to calculate the field where at point P. Let's see that what all we can do now. Let this angle be theta. This will become theta by 2, theta by 2. This angle will become alpha. This is very important. And let this be R bar. And here a current I is flowing. So what is the angle between IDL bar and R bar? Is alpha. And one more very important thing, theta by 2 plus alpha equal to pi by 2. These are very important. Actually, I should leave these things, such things for students to work out, because the application of maths will get into picture. And one more small rough diagram. This is the theta we defined. This is d theta, this is dl, this is r. So what is dl is equal to r d theta, current element. And the current I is flowing. So all these things are going to help us a lot. Okay, let's write the Magnfield at point P due to this current element. So what is the Magnfield strength? Should be equal to dB, P is equal to mu naught high dl sine alpha 4 pi r square. Now what is alpha? Angle between current element and R bar. Hope everyone is able to get this. This is the angle between current element and R bar. R bar is a position vector. And current element will be like this, and it will be tangential to this circle. So therefore, theta by 2 plus alpha should be 90. So I'll replace alpha. Now what to replace with? I think you have a triangle. Anybody value of R? What shall I write R? Small r. 2r by sine theta by 2. Or 2r cos theta by 2. From the triangle, small r equal to 2r by cos theta by 2. So this will become 2r cos theta by 2. dl, okay, sine alpha. I'll replace all one by one. D theta. Sine alpha will be sine of 90 minus theta by 2. Mu naught I r 4 pi here 4 r square cos square theta by 2. Sine of 90 minus theta. Anybody? Cos theta. One r will get cancelled, so mu naught I. This will become 16 pi. D theta is there, no? Mu naught I. What should be the limit? Check one's calculation. Anybody value of this? What should be the limit? This is very important. I want the limits also. Theta, this is theta equal to 0 degree line. This is theta equal to pi by 2. This is theta equal to minus pi by 2. I think limits also matters a lot. So therefore the limits will become minus pi by 2 to plus pi by 2. Anybody value for the simplification of this? I have final answer. Integral of secant theta d theta. Just simplify and just give me the final answer. Anybody final answer? Response from this section is very least, especially calculations, mathematics. Okay, I'll write final answer. Nobody is interested to respond. This will be your final answer. Okay, like this, we can calculate the magnetic field strength at a point P. So these are some math-based questions here to really explore things. Of all very important, this angle between current element and position vector, you have to be alert. That is what the troublesome will come. Please do take care the numericals whenever you are calculating the field strength, especially because the current element and position vector, they are vectors. So the angle between them has to be substituted here. So what is alpha we should define? Angle between current element and R bar. In every numerical of this kind, so this angle matters a lot. It has to be defined and it should be replaced with quantities where you can integrate with it, because we brought in terms of theta, because alpha integration is not possible. So what we are doing, that alpha in terms of theta has to be, I think like this, we have some plenty of questions. Do try to think. This one methodology is what I'm showing it. Like this, you can find out field at some well-defined point, not everywhere. So, sir, can you find out field here? I think we have to struggle with the geometry. We can find out field here. Polar coordinates, if you take it, you can define field anywhere at the arbitrary point. Cartesian coordinates, little bit restricted, only at some well-defined places, the mathematics will permit here. Okay, so we'll do one thing. We'll end up the class. Tomorrow we'll discuss the numericals on the Ampere's theory of Ampere's circuit law. Then I'll come with the numericals. Ampere's circuit law is nothing but the extension of Biot-savart law, like how in the electrostatic, the Gauss law, how it helped a lot in calculating the electric field due to various charged objects. Similarly, the Ampere's circuit law will help us a lot in getting the magnetic field due to various current carrying structures. So this Biot-savart law, it is having some limitation. That limitations tomorrow we'll explore. Then we'll go for the Ampere's circuit law. Meanwhile, try to practice all the problems of Biot-savart law. Few more are there. In the Friday, I'll try to cover them, all their application problems, somewhere or more on the calculus-based things. On Friday, I'll cover it. Okay, thank you all of you. Take care.